Hey everyone. So welcome to this session where we are going to be covering the chain rule, right? And the chain rule is the key to the backpropagation method or algorithm, which is what is used to train uh, deep learning models and neural networks. So if you're not familiar or just looking for a refresher, let's hop in. So let's start with an example, right? Before I introduce the actual rule, right? So these are simple expressions. You have a variable x, right? Meaning it can have any value. We're saying 3x plus 2 is equal to a value of a function y. Okay. Now we have a second expression, right? And y actually turns out to be a variable in this expression where we say 5y squared plus 1 is equal to z, where z is another function. So what we have here now, you see, is that z is dependent on y, right? It's a function of y squared, and y is dependent on x, which means z is actually dependent on x, right? Depending on how x changes, z is going to change, even though x doesn't really explicitly show up in this equation. So it's an example of implicit dependence, right? It's actually dependent, but it hasn't shown up in this equation. Now, what if we want to measure how z would change if x changes, right? Now, if you remember the previous lecture on differentiation, right? We had done a review on that. And so if you've not taken a look at that and want to review differentiation, please go ahead and take a look at that, right? We cover differentiation and what a derivative is, and we compute quite a few derivatives as examples, right? So you can go take a look at that if you want to revise derivatives. But coming back to this problem, what happens if I perturb x a little? How does z change, right? And we want to understand that. The context being that in a neural network, or in an optimization problem, you want to change a variable and you want to understand how the final output that you care about in the neural network or loss function changes as the variable is. So what do you do? So we basically trying to compute the sensitivity, which is the derivative of z with respect to x. But x doesn't show up in this equation directly, right? So think about it for a second. I'm pretty sure you're already figuring out a simple method, right? We're going to do, which is called the method of substitution, right? What are we going to do? We're going to say, well, we know y is a function of x. We've got this function, right? What if we just substitute this expression here, right? So we say z is 5 times. Now, in terms of y square, we know y is 3x plus 2. We substitute that 3x plus 2 squared plus 1. We've done that. Now, what we can do is expand, right? So a plus b the whole square is a square plus 2ab, 3 times 2 times 2, 3 times 4 is 12, x plus b square plus 1. Now simplify this. It's basic algebra. Go ahead and give it a shot. But you effectively should get this, right? So you've got this expression for z now in terms of x. This was in terms of y. You've got it in terms of x. Now you can differentiate. So you do dz by dx, which is d by dx of this expression now, right? So it's a function of x directly now, explicitly. If you remember how we did derivatives, while you first split this using some rules, so d by dx of 45x squared plus d by dx of 60x plus d by dx of 21. I'm doing this step by step so that in case you haven't gone over the previous lecture in differentiation, and well, you can follow this. Now we know d by dx of 45x squared, it's polynomial rule. It's 2 times 45 times x, right? So it's 90x. D by dx of 60x, you can take the constant out, and the derivative of something with respect to itself is 1 plus 60. And the derivative of a constant with respect to a variable is 0, right? Because no matter how you change this variable, the constant's not changing. So that's that. Now, okay, so that was okay, but the expression there was simple. What if you have a more complicated expression? So let's look at this, right? Now, y is 3x squared plus 2, but z is 5 times sine y plus 1, which means if you expand this, you're going to have to say sine 3x squared plus 2, right? Now you're differentiating 3x squared, sine of 3x squared plus 2. It's a complicated derivative. Right? Another example of how things can get complicated, what if it's just a very, very big chain of functions? So you have y, which is a function of x, and you have z, which is this complicated function of y. Then you have m, which is a even more complicated function of z, right? It's got a hyperbolic tangent and an exponent. And then you've got k, which is a function of this m, and you want to find the derivative of k with respect to x, right? You have a neural network, you have multiple layers, right? For example. So now, if you start substituting here, you're going to end up with an expression that's going to be very, very complicated. You're going to have trouble getting an analytic derivative. Okay? So what do you do? So, well, the chain rule comes and saves us. What does the chain rule say? So the chain rule says that if you have a function z that is dependent directly on y, and you have a function y that is dependent directly on x, there isn't any other way this dependence comes in it. So the dependence of x comes in through y. Then you can say that the derivative of z with respect to x is the derivative of z with respect to y times the derivative of y with respect to x. So what does this mean, right? Let's look at it. Well, let's look at the example, right? So it's the same example we saw. I'm just writing it out a little more clearly. We're saying y is a function of x, is 3x plus 2, right? And we're saying z is a function of y. Now, instead of x, f, I'm just using g, but it's a function of y, right? That's what the implication here is. And it's 5y squared plus 1. There's no other direct dependence of x. So what we do, we follow this rule. We're saying dz by dx can be given by dz by dy. So we take this z and differentiate it with respect to y. It's quite simple, right? It's 5y squared. It's a simple polynomial. So d by dy of 5y squared plus 1. So this term goes to 0, the derivative of a constant. This term, it becomes 5 times 2 times y is 10y, right? Because it's a polynomial. So something to the power of n, the derivative of that is n times that to the power of n minus 1 with respect to the same way, right? Okay. So we've got this first part. Now we say, so we've got dz by dy. Now we have dy by dx. Well, we know y is directly dependent on x. So we say dy by dx is d by dx of 3x plus 2. Again, derivative of a constant goes away. The d by dx of 3x is 3. And what chain rule tells us is you can now say dz by dx is dz by dy times dy by dx, which means it's 10y dz by dy. We've just computed that here, right? Times dy by dx, which is 3. We've computed here, which is 30y. Right? So we've got dz by dx is 30y. Now it looks a little different from what we had previously, right? Why? The answer is simple. This is in terms of y. That was in terms of x. What do you do? Well, you already know y, right? Y, we already know 3x plus 2. That was the question. So you just substitute here for y. It becomes 30 times 3x plus 2. 33 is 90. X plus 60. Just go back and check, and that was exactly the answer we got. So instead of substituting and then differentiating the whole thing, we've just differentiated this with respect to x, differentiated this with respect to y, and used chain rule to multiply. Now, this obviously the derivatives are simpler, but now when you have a more complicated case, like the multiple big chain we saw there of expressions, or if it's a sinusoid or something like that, you can see how this becomes so much simpler. There's another kind of scenario exactly for the same set of expressions we're using where it becomes even more easy, right? So for example, let's say we want to compute this derivative, right? dz by dx at a very specific x equal to 2. So you have an input. So the previous example, right, just to bring that back, it was a general expression. I hadn't given you a value for x. But if you want to be specific and say, actually, at x is equal to 2, what is the sensitivity of z with respect to x? Even better, right? So you know it's at x equal to 2. Now, what I'm going to do first is I'm not differentiating, right? We've already done that. So let's not worry about that. I'm just going to first compute the value of y and z given x equal to 2. How do you do that? Well, you substitute x is equal to 2 in this expression first. So you get 3 times x, which is 2, plus 2. 3 2s are 6, plus 2 is 8. You take this 8 and substitute it here now to get z. So z is equal to 8 square times 5 plus 1. 8 square is 64. 64 times 5 plus 1. You can do the math. It's 320 plus 1, right? Which is 321. Now what are we doing? We're saying I want the derivative, right? This is great. I've got z, but I want the derivative. So what am I going to do? I'm going to say, well, I'm going to apply chain rule. I'm not recomputing this for you. We've already done dz by dy is 10y. We've just done it, right? The previous slide or page. And dy by dx is 3. We've already computed that dz by dx was 10y times 3 or 30y. What we did there was substitute this 3x plus 2. If you know it's x is equal to 2, you've already got y is equal to 8. You just substitute y is equal to 8, right? And so you've got the answer. So in a scenario where you know x, you do a computation for z first. You actually don't care about z, you actually only care about the value of y, right? So you can actually stop here, it's an example of a forward pass, right? And you will see that as we do more we'll do a more interesting example for that. But effectively, it's a forward pass. We've computed y and we've computed z. Then what we have done is said, well, I know the derivative of z with respect to y. Simple, just differentiate this with respect to y, differentiate this with respect to x, multiply, but now I don't need to substitute this expression. I just have the value of y. I substitute that straight and I get the answer. So it makes things so simple, right? And you can already start seeing how in an example of a chain of expressions, right? Whether it's a graph, whether it's a neural network or just a connection of expressions, a chain or a tree of expressions, how this rule really becomes powerful. Okay, so let's do another example. Let's say a good application or example of scenarios where chain rule is used, right? So we're computing the exponent of 3x squared plus 2x. We've got this. We want to find the derivative of this with respect to x. Now, there is the basic rule for exponent is the d by dx of e to the power of x is e to the power of x. But what happens when it's d by dx of e to the power of 3x squared plus 2? Right? Well, use chain rule. Say, let a y is equal to 3x squared plus 2x. I'm just creating a variable y and I'm saying that's equal to 3x squared plus 2x. So now what is e? What is this term, right? Well, I'm saying I'm going to call this z and I'm saying z is e to the power of y because y is 3x squared plus 2. So z is e to the power of 3x squared plus 2, right? Following me till now, right? Basically, if you substitute y here, you get e to the power of 3x squared plus 2, which is our question. Now what do? I want to compute the derivative of this with respect to x. I say dz by dy. Derivative of z with respect to y is d by dy of ey because we're computing the derivative with respect to y now, not x, right? So d by dy ey is e to the power of y, right? Simple. That's the standard rule for exponent. You can check out the notes or you can check out the lecture on differentiation. This is the answer. dy by dx, again, simple. It's a polynomial. So it becomes d by dx of 3x squared plus 2x. Differentiation of this is 6x, right? 3 times 2 times x plus the derivative of this is 2. So now, chain rule, dz by dx, which means the derivative of this with respect to x, is dz by dy, which we already have is e to the power of y, plus in times dy by dx. So e to the power of y times 6x plus 2. Now you can stop right there, but given we want this in terms of x, it looks better if you've got the derivative with respect to x in terms of x, right? So you substitute for e to the power of y, you substitute for y there because we've created that variable. So I'm just going to rearrange the way it looks. I'm going to take 6x plus 2 outside and say e to the power of y. So to the left-hand side, that is. And substitute for y. Y is 3x squared plus 2x. Got that. So this is now the derivative of this expression. So that also, what does it do? It gives us a way to compute the derivative of slightly more complicated expressions by using something as simple as chain rule, right? You see how powerful this application is. Okay. Now let's tackle something fairly interesting to our context, right? Which is deep learning. So you've got this chain of expressions. We've already looked at an example there, right? Where we were trying to show why substitution is complicated. Well, here's a good one. D is 2a plus 5. And all of these A, generally we use A, B, C, D and stuff as constants. In this case, I'm using it as variables, right? So D is 2a plus 5. C is 3b minus 2. F is C times D plus 8. And G is now F squared plus 2F. So fairly complex. And I want the derivative of G with respect to A. I want to know how A impacts G. So what we're going to do is, and you can actually try substitution. I'd encourage you. It will be a good way to revise your math. But what I'm going to do is we're going to build a tree or a chain of expressions. I'm calling it chain because we're applying chain rule, but I'm going to, even it's a tree, right? And you could draw a tree this way. I'm just keeping it simple again to help you correlate with a neural network, right? Which is our actual goal in the long term. So I'm saying an input A is an expression here. D is 2A plus 5. These circles indicate some computation and it's giving out D. Take another one for B. C is 3B minus 2 and it gives you C. What happens next? We have F. So F is C and D, CD plus 8. F comes out and we're left with G. G is F square plus 2F. And G is what comes out. So you see how this chain works, right? The output is G. The inputs are A and B. A first goes here, 2A, and it becomes 2A plus 5, which gives us D. C goes through this, well, B goes through this and becomes C with the expression 3B minus 2. C and D here become F through the function CD plus 8. And then that F now becomes G, right? Because it's F square plus 2F. So it's a chain or a tree of expressions that are connected. Now we want the sensitivity or the derivative of this with respect to A. How does G change when A is perturbed or modified? So we're going to take this chain, and what we're going to do is we're going to use chain rule, right? That's the title of the lecture. So what is chain rule? Well, dg by dA, just trace this path back, right? dg by dA is dg by df, because G is here and F is the only variable that shows up there, right? So dg by df. Then here we're only interested in A. So forget this link. We're going to focus here. We're going to say df by dc, right? We're assuming that here there's no dependence of A, and you can see here there is no dependence. B is not dependent on A, so D is not dependent. So we have df by dc, and then dc by dA, right? So it makes sense. And now we've got three expressions, but chain rule applies, right? So now let's compute this. So we start here. I like to work backwards. You could also go this way, say dc by dA, df by dc, and dg by df, and work this way. I prefer working this way also because it also, kind of correlates with backpropagation. So I like that idea. So you have dg by df, right? Well, g is f square plus 2f. D by df of f square plus 2f is, well, so take the first term, d by df of f square plus d by df of 2f. Derivative of this is 2f and the derivative of this is 2, right? D by df of f square is 2f. D by df of 2f is 2, right? Simple. Again, if you have an extra screen, you can keep or on the side, you can keep, the note of, or the basic, cheat sheet of derivatives, which we had given you in the derivatives session, or they're also there and on the notes at pixicon.ai. So you can use that, or open up Wikipedia and you'll get these derivatives. So now next, we've done this. Now we're here. So now what we need is df by dc. Right? So it's d by dc of cd plus 8. We know d is not dependent on c. This is a constant. So this term goes away. And this is, you take the d out because d is not dependent on c. And you get d. Right? Simple. You're following? And then the last term, dc by dA. So d by dA of 2a plus 5. Again, we've broken it down with some rule. D by dA of 5, derivative with respect of a constant, goes away. D by dA of 2a is 2. So we've got dg by df, df by dc, and dc by dA. So what are we going to do next? Well, I'm just taking out the steps and showing you just the answers. We want dg by dA. So chain rule tells us, we've already looked at this, dg by dA is dg by df times df by dc times dc by dA, which is 2f plus 2 times d times 2, which is 2d times 2f plus 2. Now I'm going to leave it to you to expand f in terms of A. That's your exercise, right? So you know f is cd times plus 8, and you can expand that. The reason I'm not doing it also is because generally in an actual application where you're computing something, a neural network, more specifically, You would have done a forward pass. You would actually have the value of f and c, right? Which, in fact, we've shown you in the first example, right? So you would actually not have to then compute or substitute for this. You would just have the value of f. You'd put that here. You'd have the value of d. You'd put that here, and you'd get the answer. So I'm not expanding it any further. So this is already starting to give you, while you've hopefully really figured out chain rule with this, with these examples, you're really starting to understand it. It's also giving you a basic idea of what happens in terms of, a neural network. And don't worry if you don't fully grasp it yet, because, well, we're going to cover backpropagation in detail. But if you've started figuring chain rule out, you start understanding how you can use chain rule to get expressions across this whole connected set of operations, then it's going to become very easy for you to follow backpropagation. So do check out the notes and the quiz, right? Do try out the quiz, especially because we put out questions for you to help you understand the ideas a little more. So that'll really be interesting. And sometimes we stuff that we haven't covered in the lecture, but it's important we put it in the notes just for you as a reference and in the quiz, right? Because it's not maybe directly relevant to the lecture, but is something that's probably good to know. And then, if you're interested, the next thing you can take from here is looking at how backpropagation works, which we're going to be posting soon, or have already, yeah. And you can also look at, how a single node learning model works, right? To understand kind of an application, which is quite simple. It isn't a full neural network, but it's another good place to kind of understand how a neural network works. So hope you've enjoyed this session and really started understanding chain rule. See you soon.